Hello friends, greetings from Professor M.I. Vyas. We are learning elements of mechanical engineering. We have already started the heat engine. We have seen in heat engine till date what is heat engine, classifications of heat engine, cycle, Carnot cycle, limitation of Carnot engine, so the engine which works on the Carnot cycle, and then we have seen the practical engine, means the engine which works on the other cycle, that is Rankine cycle, Otto cycle, diesel cycle. Last time we have started just the Rankine cycle. Today we are going to analyze, we will carry out the analysis of the Rankine cycle. So, Rankine cycle, this has two differences to the Carnot cycle. There must be a reasonable temperature differences in the boiler and condenser to ensure that heat addition and rejection occurs at an acceptable rate. And second, the turbine exhaust is completely condensed and returned to the boiler by pump. This uses very much less energy than a compressor. See what the difference? There must be a reasonable temperature difference in the boiler and condenser. So if there is a sizable delta T, then heat addition will take place in the boiler and heat rejection takes place in the condenser. So temperature difference is important. And second, we are using pump in place of compressor where we used in Carnot engine, and the pump consumes very less energy. Second, this results in the lower efficiency than the Carnot cycle, but permit the useful work to be done. So what? See, efficiency will be less. This Rankine cycle efficiency will be less, but at least some useful work will get, or the useful work to be done. Let us see the Rankine cycle. In Rankine cycle, there are four components. I will draw first the diagram, the flow diagram of Rankine cycle. These are the four components. This is the path of working fluid. This is boiler. This is turbine. This is condenser, and here it is pump. What happen in boiler? We are supplying the heat. How that heat? Basically that is fuel we are supplying. Also there is a water and air supplying. Combustion of fuel takes place, generate the steam. High pressure, high temperature steam leaves the boiler. So and enter into the turbine. Let us say this is point 1. Steam in the path. The turbine where high pressure, high temperature steam enters, expansion of the steam takes place. As a result, you will get work developed by the turbine, or you can say the output by the turbine at the turbine shaft, and the low pressure, low temperature steam leaves. This is at point 2. Low pressure, low temperature steam enter into the condenser where some cooling medium is moving, so the steam reject the heat. Let us say this is here heat rejection. Heat rejection takes place. Steam convert into the water, leaves the condenser through the pump where it feedbacks to the boiler. So here it is the pump work, that is WP. Here it is heat rejected, say QR. Heat addition, it is here QS. We are interested to carry out the analysis of the Rankine cycle. So this is flow diagram of Rankine cycle. Draw PV diagram. We will draw PV diagram. This is point 1 to 2. Expansion of the steam takes place in the turbine. This happens in turbine 1 to 2. 2 to 3. This in condenser 2 to 3. So 2 to 3 is here. This is here point 3. Heat rejection. From 3 to 4 through the feed pump we are feeding back to the boiler. So three, 4 feeding back to the boiler. 4, 1 through the boiler heat addition takes place. Four to 1 heat addition takes place at constant pressure. So you have two pressure limit over here. P2 is equal to P3, and here P1 is equal to P4. Let us see 1 to 2 expansion of steam into the turbine, 1 to 2 expansion of steam into the turbine, 2 to 3 heat rejection takes place in condenser, 2 to 3 heat rejection place in condenser at a constant pressure, 3 to 4 through the pump heat addition takes place, 3 to 4 pump supply to the boiler, pump supply the water, feed back to the boiler, that is 3 to 4, and 4 to 1 is the heat addition takes place in the boiler QS, that is at constant pressure. The same diagram on TS. The same process on TS chart. This is point 1, point 2, 3, 4. This is in turbine. 1 to 2 in turbine, here it is 2 to 3 heat rejection, 2 to 3 heat addition in condenser. This is in condenser. 3 to 4 pumping work, so that is through the feed pump back to the boiler in pump. 4 to 1 heat addition, 4 to 1 heat addition, that is here. First, this is the sensible heat, latent heat of evaporation, and this is the heat of superheat. This entire process carry out in a boiler. So this is the flow diagram, and this is the property diagram. Property diagram, two types: PV and TS, pressure, volume and temperature entropy diagram. We are interested to carry out the analysis to find out the Rankine cycle efficiency. See, analysis of Rankine cycle. We have seen, let us see what the first is: process 1-2. Process 1-2 happens in turbine. What happen in turbine? Expansion of steam takes place. This expansion of steam takes place. As a result, work is developed by the turbine. Work is developed by the turbine. Let us say it is W2. So WT is nothing but H1 minus H2. H1 minus H2 kilojoule per kg. This is the turbine work developed. Then process 2-3. Process 2-3 occurs, happen in condenser. What happened in condenser? Heat rejection takes place. Heat rejection takes place, that is QR, at constant temperature. So heat rejection QR, you will have QR is equal to H2 minus H3 kilojoule per kg. Then the next process, once the steam leaves the condenser through the feed pump process 3-4, it happens feed pump with the help of feed pump. What happen? Water is feed back to the boiler. Pressure moves from P3 to P4. This pressure P4 is known as boiler pressure. This is known as boiler pressure. Work of pump, that is H4 minus H3 kilojoule per kg. So work of pump kilojoule per kg. Then it comes 4, the process 4-1, it happens in boiler. Heat addition or supply of heat takes place. Heat addition takes place this QS is at constant pressure. Heat addition is at constant pressure. So, what is heat addition? Qs is equal to H1 minus H4. Qs is H1 minus H4 kilojoule per kg. So once again, process 1-2 in turbine, expansion of steam, work developed by the turbine H1 minus H2. Process 2-3 condenser heat rejection, QR at constant temperature as well as constant pressure. This is as well as constant pressure. That is QR is equal to H2 minus H3 kilojoule per kg. Process 3-4 in feed pump, water is fed back to the boiler, pressure increase P3 to the boiler pressure P4, work of pump H4 minus H3, and process 4-1 in the boiler, heat addition takes place. Qs at a constant pressure. Qs is equal to H1 minus H4 kilojoule per kg. Now, net work developed is equal to turbine work minus pump work is equal to turbine work is H1 minus H2 minus pump work is H2, pump work is H4 minus H3. As compared to this turbine work, pump work is very small compared to turbine work. Pump work is very small. Pump work is very small, so neglected. So W net you can take it as H1 minus H2. H1 minus H2. So Rankine cycle efficiency is equal to net work upon heat supplied. Net work H1 minus H2, so eta R is equal to H1 minus H2 upon heat supplied H1 minus H4. This is the Rankine cycle efficiency. So friends, we have seen that Rankine cycle, these four are the component: turbine, condenser, pump and the boiler. Working fluid is steam which continuously move. From here it is steam, from here onwards it is water. This is PV diagram, temperature entropy diagram. We have seen the analysis, what happens, and ultimately get the efficiency of Rankine cycle H1 minus H2 upon H1 minus H4. We'll further move to another cycle. That is Otto cycle. Otto cycle. Otto cycle is what kind of the cycle? It is constant volume cycle. Scientists namely Nicholas A. Otto, who was the German fellow, developed this engine working with this cycle, and that is why the name is given to the Otto cycle, where in this cycle heat is supplied and rejected at constant volume. Heat is supplied and rejected at constant volume. Hence, it is called constant volume cycle. We are interested here in this Otto cycle. We'll see it is a constant volume cycle. We will see the air standard efficiency and we will carry out the analysis of this cycle. Let us first see what is air standard efficiency. Air standard efficiency. What is air standard efficiency? When the efficiency of an engine in which air is used as working substance, then it is air standard efficiency. The efficiency of an engine in which air is used as a working substance is air standard efficiency. So, what is that? At standard efficiency is always greater than the actual efficiency of a cycle. We are interested here in Otto cycle. Let us see what is the Otto cycle. So this is PV diagram for Otto cycle. Let us see the analysis, what happens. Process 1-2. Process 1-2 here. It is isentropic compression of air. Isentropic compression of air. So air enters, piston moves, compression of inside that in cylinder, the compression of air takes place. Process 1-2, volume reduced from V1 to V2. As a result, pressure increases from P1 to P2. From P1 to P2, pressure increases. Then we see the process 2-3. Process 2-3, heat addition takes place. Heat addition takes place, that is at constant volume. At constant volume, heat addition at constant volume. Process 2-3, heat addition takes place. We are supplying the heat. Let us say it is QS, constant volume, V2 is equal to V3. The process 2-3 carried out, V2 is equal to V3, constant volume. Process 3-4. Process 3-4, reversible adiabatic, that is isentropic. Reversible adiabatic, that is isentropic. Expansion of expansion of air. So that is process 3-4. 3-4, expansion of air takes place. And the process 4-1, it is heat rejection. Heat is thrown out. Heat rejection, that is again at constant volume. That is process 4-1, heat rejection at constant volume. Heat is rejected, QR, at constant volume. So after doing this analysis, or you can say the understanding of these four processes, that is process 1, 2, compression of air takes place, volume reduces, pressure increases. 2, 3, heat we are supplying, the addition of heat takes place at a constant volume. 3, 4, expansion of air takes place. And 4, 1, heat rejection, constant volume. During this time, process 1, 2, when it is 1, 2, piston move inside, heat addition takes place, expansion, piston moves outside. So, understanding will help us to derive the efficiency of the cycle. We are interested into the efficiency of the cycle. What is the efficiency of the cycle? First, it is air is used. It is air standard efficiency eta is equal to net work done upon heat supplied or heat added. In the process where the heat addition takes place, we can write it is heat addition QS at a constant volume is equal to M into CV T3 minus T2. Heat addition T3 minus T2 and heat rejected is QR, that is equal to M into CV T4 minus T1. This is the heat rejected. What is net work done? Net work done is equal to heat supplied minus heat rejected. Heat supplied minus heat rejected. Heat supplied minus heat rejected is equal to MCV T3 minus T2 minus heat rejected MCV T4 minus T1. Hence, efficiency is equal to MCV T3 minus T2 minus M into CV T4 minus T1 upon heat supplied, that is MCV T3 minus T2, that is MCV T3 minus T2. If we rearrange and simplify, it comes 1 minus T4 minus T1 upon T3 minus T2. So we have seen that efficiency is equal to 1 minus T4 minus T1 upon T3 minus T2, because the equation which net work upon the heat supplied we have simplified and we reach to this. Now here two important things. We are interested the compression ratio. We are interested in compression ratio. Compression ratio is defined as R. Compression ratio is defined as R. Compression ratio. What is compression ratio? It is the ratio of total cylinder volume to clearance volume is called compression ratio. So cylinder volume is equal to Vc plus Vs, where Vc is the clearance volume. Vc is clearance volume and Vs is the swept volume, or you can say the stroke volume. For this entire compression ratio, Vc and Vs, you will more detail in learn during the IC engine. In our case, cylinder volume, we are taking Vc plus Vs. So you can say that R is equal to Vc plus Vs upon Vc. Vc plus Vs upon Vc. In our case, if we refer the figure, if we refer this figure, you can say that this volume V2, this is clearance volume. In our case, this is clearance volume, and during this piston moves in and out. So this is the swept volume. This piston moves in and out this process and comes out in this process. During this process it moves in and here it moves out. So this is the stroke volume or the swept volume. So we can say that in our case, you can say that in our case V1 is equal to Vc plus Vs and V2 is equal to Vc. Hence R is equal to V1 upon V2. Similarly, expansion ratio is equal to R is equal to V4 upon V3. Here V4 is equal to V1, so it is V1 plus V3. You can say that V4 is equal to V1 and V3 is equal to V2. So R here it is V1 upon V2. So for process 1 to T2 upon T1 is equal to V1 upon V2 raised to gamma minus 1 is equal to R raised to gamma minus 1. For process 3-4, you can also have a T3 upon T4 is equal to R raised to gamma minus 1. Put all this value in our efficiency equation. So and by this you can get T2 upon T1 is equal to T3 upon T4 is equal to R raised to gamma minus 1. In efficiency equation, if you put, you will have eta is equal to 1 minus T3 upon R gamma minus 1 minus T2 upon R gamma minus 1 divided by T3 minus T2. If you simplify this, you will get is equal to eta efficiency is equal to 1 upon 1 R raised to gamma minus 1. Eta is equal to 1 minus 1 upon R raised to gamma minus 1. So what we can conclude? Efficiency is equal to 1 minus 1 upon R raised to gamma minus 1. You can conclude that the efficiency is depend on depends on the ratio, compression ratio. This is the conclusion. So friends, today we have learned the Rankine cycle, its analysis, Otto cycle and its analysis. Next time we will do some numerical problem based on these two cycles, as well as we learn one new cycle. You refer the good books, read out. My wishes and prayer for you, for your success. A very all the best from all of us here. Thank you.